Good morning, my YouTube viewers. It is Crystal here. And this particular video, what we're going to be talking about is the Latin square design, which is a type of experimental design. So a Latin square design is a design that accounts for two blocking factors, such as rows and columns, ensuring each treatment appears exactly once in every row and column. And so you've got an example that we're going to go over. We're going to have 4 treatments over 4 rows and 4 columns. The null hypothesis is no significant difference between the rows and columns. And the alternate hypothesis is there is a significant difference between the rows and columns. So what we're going to do is we're going to review the code of a Latin square design. So the first thing we're going to do is we're going to create our Latin square layout, which is a 4x4 matrix. So Latin becomes matrix, which is a vector of A, B, C, D, B, C, D, A, C, D, B, A, B, and D, A, B, C. And so there's going to be 4 rows, and by row is true. And then we're going to look at the matrix that we've created. So we're just going to look at the matrix that we've created. So this is the matrix that we've created. So A, B, C, D, B, C, D, A, C, D, A, B, and D, A, B, C. So that's what we've created in this Latin square design. Now we're going to simulate the data for the Latin square. So the first thing we're going to do is set our seed. And the reason why you set your seed is so every time you run the program, the variables are going to be initialized to the same values. So you type set.seed brackets 1, 2, 3, and you can put any number you want within the brackets. So the treat effect becomes a vector, which is A equals 10, B equals 12, C equals 14, D equals 16. The row effect is a vector of 0, 1, negative 1, 2. The column effect is a vector of 0, negative 1, 2, 1. And the response is a numeric list, a numeric array with 16 elements in it. So the response is a numeric list or a numeric vector or a numeric array with 16 elements in it. And you get that 16 by you multiply 4 times 4. So the treatment becomes as.vector Latin. That's your treat. Your row is factor of a repetitious vector, a repeated vector of 1 to 4, 4 times. So you have 1, 2, 3, 4, 4 times. A column is a factor, which is a repeated vector of 1 to 4, 4 times. So that's going to be 1, 2, 3, 4, 4 times. And then so now we're going to create a for loop for I in 1 to 16. Because you know you've got the number of elements in the response is 16. And 4 times 4 is 16. So I in 1 to 16. And so if you're accustomed to programming in Python, remember that the first number in Python is 0, but the first number in R is 1. So response I becomes treat effect brackets treat I plus row effect brackets row I plus call effect brackets call I plus R norm, which is a randomly sampled normal distribution of 1 sample with a standard deviation of 1. And then so we're going to create a data frame with all this information. So dat becomes data.frame brackets row, comma, call, comma, treat equals factor, treat, comma, response. And then so we're going to look at the data frame that we have created. So this is our data frame. It's got 16 rows by 4 columns. So you've got your row, which is 1, 2, 3, 4. You've got your column, which is 1, 2, 3, 4. You've got your treatment, which is A, B, C, D, B, C, D, A, and onward. And then you've got your response, and I think that's a mean. So you've got 16 rows, and it shows you the complete data frame. So now we've got our data frame. We created our data frame with all of this information. And then after we've created the data frame, what we're going to do is we're going to conduct an experiment using the ANOVA model. And you have 2 types of ANOVA model. One type of ANOVA is for performing hypothesis tests. And the second type of ANOVA is when you're using it within a linear regression model. So in this test, we're going to use the ANOVA within a linear regression model. So FIT becomes AOV, that's ANOVA, which is short for analysis of variance, brackets response, that's your Y variable or your dependent variable in a squiggly sign. I think they call it a tilde. And treat plus row plus column. So that's going to be your independent variable or your X variable, and data is going to be data. And then you've got summary fit, so we're going to summarize the model. So we're going to look at our model. So you've got treat, row, call, residuals. So you've got your degree of freedom for treat, row, and call is going to be 3. The reason why is you've got 4 of everything, 4 by 4, and then you calculate your degree of freedom by taking the number of elements or the number of samples and subtracting 1. So for treat, it's 4 minus 1. For row, it's 4 minus 1. For call, it's 4 minus 1. And then for residuals, you're taking the total number of elements, which I think in this instance is going to be 16. And then we're going to 16 minus 10 is going to be 6. But I think, so 16 minus, but it comes up with 6 residuals. And then you have your sum of squares, you have your mean squared error, and then you have your F value, and then you've got your P value. So the P value for treat is 0.003. The P value for row is 0.09. The P value for column is 0.06. So for the row and the column, the P value is going to be greater than our significance level of 0.05. So for the row and the column, what you're going to do is you're going to fail to reject the null hypothesis. But for the treat, that is less than 0.05, less than your significance level. And so you're going to reject the null hypothesis in favor of the alternate hypothesis. And you've also got your significant codes as well. So that's what we got here. So now what we're going to do is we're going to plot our answers. So we're going to plot the treat means with 95% confidence interval. T means becomes T apply brackets dat $ response, comma dat $ treat, comma mean. And then TSD becomes T apply brackets dat $ response, comma dat $ treat, comma ST, that's your standard deviation. And N per treat becomes 4. So that's each treatment appears 4 times. So your CI lower, that's your lower confidence interval, becomes T means minus 1.96 times TSD divided by square root of N per treat. And so we already know the N per treat is 4. And then CI upper is the upper confidence interval, and that's t-means plus 1.96 times TST divided by square root of n per treatment. And then so now what we're going to do is we're going to define the variable centers, which is the bar plot, brackets t-means, comma, y-lim, that's your limit on your y-axis, equals c-min, ci-lower, times 0.9 times max ci-upper times 1.1. Color is a vector, steel blue, tomato, gold, and sea green. Y-lab, that's label on your y-axis, is response. And main is the title of the plot. It's Latin square design. Treatment means with 95% confidence interval. And now we're going to make some arrows. Arrows, brackets, centers, comma, ci lower, comma, centers, comma, ci upper, comma, angle equals 90, comma, code equals 3, comma, length equals 0.08, comma, line width equals 2, PAR, brackets, MF, row equals a vector of 1 to 2, plot, brackets, fit, comma, which equals 1, plot, brackets, fit, comma, which equals 2, and par, brackets, MF row equals a vector of 1 to 1. So now what we do is we run the program, and this is our Latin square design. Treatment means with 95% confidence interval. So you can see that you've got A, B, C, D. So the means of A, B, C, D are progressively higher. So the values are progressively higher. And then so you've also got your confidence intervals as well. But when we look at the data that we've created, data that we've simulated, so you can see mean of A is 10, mean of B is 12, mean of C is 14, mean of D is 16. So you can see that the means have become progressively higher, and the confidence intervals have become progressively higher as well. And then we're also going to look at our we're going to look at our diagnostics. That's what it's called. It should say here, but it doesn't say that. It should be diagnostics. So that's your diagnostics. So we're going to look at our diagnostics. So here's our diagnostics. So your residuals versus your fitted, and then you've got your QQ residuals based on a normal distribution. So that's your diagnostics as well. So you've got your fitted values and your theoretical quantiles, which you've made with the QQ plot. So that's it for this video. Let me just see. And the next video, we're going to be talking about another experimental design. And so I really do hope that you got something out of this video, and I hope that you watch the next video as well, which is going to be another topic on experimental design. So thank you for watching this video, and I look forward to communicating with you in the next video.